So it is Oleg Lavrentovich from USA.
First of all, thank you for the opportunity to present our results at this nice conference, and thank you for making this online presentations going seamlessly. I would like to talk about our work on how to use liquid crystal elastomers or liquid crystal polymers to control living tissues. The motivation for this work stems from the recent developments in biomedical field in which people are trying to grow organs and tissues. Here you see the microscopic images of examples of those microorgans, such as a small heart on the bottom left and a small stomach on the right. And if you look carefully, you would realize that one of the main ingredients in those organs is orientational order of elongated cells. Here, for example, in this stomach, you see some needle-like cells that are arranged along the organ with some orientational order. And for those of us who are used to work with liquid crystals, this is reminiscent of how the molecules of liquid crystals are arranged in space. And here I show a texture of a pneumatic liquid crystal that is strikingly similar to the arrangement of cells in a microorgan. Of course, it's very kind of premature to say that we can grow anything by using liquid crystals, but the unifying feature, orientational order, suggests that some things would be possible in the future. This slide shows the more concrete example. It's an epithelium, something that is involved in the structure of our skin. And the recent work published in Nature about 3 years ago demonstrated that, in fact, the structure of epithelium is identical to that of the so-called pneumatic liquid crystal. So what you see on the left-hand side is the piece of the epithelium, and you see this elongated cells. And the cells form a pattern that is orientationally ordered. And in this pattern, you might see topological defects. Taras Turyev introduced you to some of the terminology. We used the terminology of topological charge. And here you might observe a topological defect of strength 1/2. This is the charge of the defect. And it is being paired with the defect of strength -1/2. The strength is or charge is simply how many times the local orientation changes when one circumnavigates around the core of the defect one. So if I go around this defect core plus 1/2, I would observe that the cells make a reorientation by 180 degrees. And here it's the same thing, but the sense of rotation or reorientation is opposite. So it's not just that the cells form a pneumatic liquid crystal, it's also that the topological defects that are formed in the tissue play a very important physiological role. It turned out that the cores of the defects of strength plus 1/2, these cores serve as the places where the dead cells are being expelled from the tissue. We know that our skin sheds out dead cells, and in this paper, researchers demonstrated that the expulsion of dead cells occurs at the centers of the defects. So we observed that the tissue has topological defects that play an important role in the functioning of the tissue. But at this stage, we don't know how to control these defects. How do we grow something in which there is an orientational order, and how do we place the defects in certain locations so that the dead cells, for example, can be extracted at those locations. And this was the motivation of the work. And in what follows, I will show you how we can create the orientational order in synthetic coatings and in living tissues, and produce the pre-designed pattern of the order and topological defects. To accomplish the goal, we are going to use the so-called liquid crystal elastomers. So you probably know what the liquid crystal is. Liquid crystal is a fluid which is made of elongated molecules. They are aligned each other along the certain direction that is called the director, as shown here. So the rubber is nothing else but a liquid crystal that was polymerized. Typically, we use light to polymerize the liquid crystal, and the ends of the molecules are being connected with each other, so that the entire structure is really a rubber. You can stretch it mechanically, but also you can play with elasticity by using external factors such as changing the temperature. Here I show what happens if the temperature of this piece of rubber is increased, because the orientational order becomes disordered when the temperature is very high. The fluctuations would make the molecules looking into different directions. The reorientation leads to changes in the elastic properties of this piece of rubber. Namely, the sample will shrink along the director and will expand in the perpendicular directions simply because of the conservation of mass. So the liquid crystal elastomers, combining the properties of liquid crystals and rubber, show a wide range of interesting elastic properties, and typically they are explored in the aligned state. For example, these two picture in the center and the right side of the slide demonstrate the principle of an artificial muscle. This rubber can shrink and expand as the function of temperature in the environment, and it's nothing else but the artificial muscle. But we are more interested in a pattern in the orientational order to make it non-uniform and to produce topological defects. So my talk will be first about how to make nano patterns out of liquid crystals, and then how to construct artificial skin that has a response to the changes of temperature, and finally, how to use the nano-patterned liquid crystal elastomers to control living tissues. Let's start with this photosensitive molecule. You see here a molecule that belongs to the class of azo dyes, and it contains the azobenzene groups that are very sensitive to light. They would realign in the presence of linearly polarized light, as shown in this picture. This alignment occurs simply because of trans to cis isomerization of the molecules, and when they are aligned perpendicularly to the polarization of light, they cannot engage into this isomerization, and so this is the stable state of the molecule. One can use the recently developed technique of photo alignment to produce a uniform alignment of these azo dye molecules by using a polarizer that represents a metallic film with nanoslits. If non-polarized light passes through such a film, then each nanoslit would produce a linear polarization of the transmitted light along the direction that is perpendicular to the long axis of the nanoslit. You can say that, well, it's nothing interesting because one can achieve linear polarization by many different means. And you would be absolutely right, except that we are interested in a patterning of the orientation, and thus we can design this meta mask with slits that follow a certain orientational pattern. For example, I show here the pattern in which the nanoslits form a topological defect in the center of charge 3/2. So when the light goes through such a nano mask, it gets polarized, and it is linearly polarized locally. And if you go from one point to another point, the direction of this linear polarization changes. And then if you use this pattern of polarized light to align the azodye molecules, they would follow the pattern and form the orientationally ordered state. And we use this state as the substrate for the liquid crystal, and then we can proceed with our goal, which is, as I said, to produce a liquid crystal elastomer with orientational pattern in the plane of the cell, and then see whether we can produce effects that are known in the medicine of skin, namely whether we can produce the variation of the profile of the coating, such as shown here with the extrusion of the dead cell. So whether we can transform the in-plane orientational field into the changes of the thickness of the artificial skin. So this is the chemistry. This is the materials that we are using. You see the acrylic ends in these molecules that allow us to polymerize the material. And let me start with two pre-designed patterns. So both patterns are kind of square lattices of molecular orientation. The only difference is that in the pattern on the left, you see mostly circular director orientation, and in the pattern on the right, you see mostly radial orientation of the director. So those are two different modes of the orientational distortions in the system. And let's see what would happen if we have such a pattern coating and change the temperature of it. So this slide shows the situation with the predominantly radial in-plane orientational order. The formula for this order is presented on the left. So when you heat the sample dramatically, you observe dramatic changes. You observe that the coating becomes very non-uniform in its thickness. Namely, the coating develops strong indentations, strong kind of holes in the structure. And as you play with temperature, these indentations either become deeper or the film comes back to the flat state. The next sample shows a totally different behavior. In this pattern, the director field experienced this circular deformations. And when you hit such a coating, then instead of indentations, you have elevations, you have peaks, mountains, if you wish, when you increase the temperature. And as you see, the effect is very robust. Each and every defect that was pre-designed in the plane of the elastomer produces a spike. You can see the still pattern here at the bottom of the slide. So the question is, what is the physics? Why do we have this dramatic difference that shows itself in either elevations or depressions of the coating? It looks like it's very difficult to explain the physics because the geometry is complex. We have different boundary conditions at the bottom of the coating, and at the top, the material moves, but but it turns out that in fact the physics is relatively simple. So let's consider the element of this liquid crystal rubber and recall what happens when we heat the material. The orientational order gets weaker, the material kind of melts into the isotropic fluid, and as a result, the element of this rubber shrinks and expands in the perpendicular direction. So this element, instead of being the elongated ellipsoid at low temperature, becomes a sphere at high temperature. So from the physics point of view, this change in the shape can be presented as simply two forces acting on the poles of the ellipsoid that try to shrink it into the sphere. Now consider what would happen if you have many elementary ellipsoids of this type and they are following the director field that is distorted, that is pre-patterned to be, for example, in this circular band geometry. If you look at the point at which two ellipsoids meet with each other, you would realize that these two forces belonging to different elementary ellipsoids do not cancel each other. Instead, they produce a resulting force shown by this black arrow that is directed somehow towards the center of the circular pattern. If the radius of curvature is smaller, then you would realize that this force is larger. And in fact, mathematically, you can represent the dependence of the force on the gradient of the director field by this simple formula. So if you would have the circular defect, then this simple argument would lead to a conclusion that the resulting force will try to move the material towards the center of the structure. If you have the splay deformation or radial deformation, then the situation is similar, but the direction of the force would be different. Here you see that the force is directed away from the center of curvature to the periphery. Mathematically, you can derive the expression for this force shown here, and you have two terms. One is splay, or it's a kind of a radial deformation, and another one is band or circular deformation. And there is a coefficient alpha here that depends on the shear modulus of the rubber. And with this formula now you can predict what would happen with the elastomer. You know your director field that is predesigned by the MetaMask, and you apply this formula to the designed director field, and you obtain how the active force behaves in different arrangements. If you have the arrangement with predominantly radial deformations, then in the center of each defect of strength +1, you would see the radial force looking outwards. And that means that the material will be depleted in that point, and you would produce an indentation. But if the pattern contains the radial deformations, then the sign of the active force is opposite, and the active force would produce more material in the center of the elastomer, and you would have the spike that grows up in the coating. It's like the goosebumps on your skin when the temperature drops significantly. So now I would go to the final part of my presentation, which is how to use these elastomers to produce the living cell. So far, we just produce a kind of analog of the artificial cell that is formed by artificial material. But now we would like to use the real tissue for the production of topological defects. So we will use human dermal fibroblast cells. Those are an important ingredient in the structure of our skin. And these molecules are elongated. You see fibroblast molecules shown here in green. So we use a liquid crystal elastomer coating that is formed when the coating is placed in contact with the water. All the cells live in water environment, and when we place a culture of the cells in contact with our Lie crystal rubber, what happens is that the layer of dye underneath the Lie crystal elastomer absorbs water and creates the kind of swelling of the Lie crystal elastomer, and this swelling produces little grains of profile, and they are not very large. They are a few tenths of micrometers long and only about 50, 60 nanometers in height. But it turns out that this is sufficient for the cells to test and to feel the profile and to align themselves parallel to those nanograins. Here the movie shows you how the cells that are being deposited from water environment above this picture, when they contact the substrate, they feel the nanograins. You see this nanograins as little ticks in this movie. And as you might see from the movie, the cells that are initially spherical, when they touch the substrate, they immediately transform into elongated cells that align themselves horizontally, parallel to the orientation of the director. Of course, since we can, this is just the same result, but shown for a longer period of time. For about 5 days, and then 10 days, that illustrates this very uniform alignment of the cells. So recall that our prime goal was to reproduce the living skin in which there are topological defects in some locations, and since we can pattern our substrate, we can design the artificial living skin in which the topological defects are located where we want them to be located. So this is very similar to the pattern that I showed before, but unlike in the previous case, now we can control the location of the topological defects. There is a very interesting feature in those patterns. If you produce topological defects of different charge, it turns out that they affect not just the orientation of the cells, they affect how the cells, the cells shape themselves. For example, the density of cells is much higher near the positive defects as compared to the negative defects. And because of that, since the cells are touching each other, what happens is that their phenotype, the ratio of the widths to lengths of the cells is very different near the positive defects and negative defects. And you might understand that the phenotype of the cells is very important for their biological function, for differentiation. And we plan to use this fact in the future to kind of create different types of the cell in different places of the orientational pattern. But an important and interesting from the physical point of view effect in those tissues with positive and negative charges is that if you have a charge of strength +1, like shown here, this circular deformation around the core, and if you wait a little bit, you would see that the defect splits into two of strength 1/2 each. And with time, they drive away from each other. As you see here, the plot shows the distance between the two half defects as the function of time. So for those who studied dislocations in solids or disclinations in Lie crystals, this effect comes as no surprise because the elastic energy associated with the defect is growing proportionally to the square of the strength of the defect. In the case of a dislocation, it's the square of Barger's vector. In the case of disconation in the Lie crystal, it's the square of the topological charge M. But then,
I'm sorry, Mr. Professor, we'll be out of time. So you got only 3 minutes left.
Yeah, this is my one slide before the end. But it turns out that if the structure is patterned in the radial fashion, then the defects actually approach each other. And so the effect is very easy to understand from the picture that again operates with force-free motion of the cells. If they are arranged in the circular pattern, the active force is going away from the center. If they are in the radial configuration, the active force moves them towards the center. And the simple physical model that connects the balance of the elastic forces and the active force allows us to deduce the elasticity of this coating and the strengths with which the orientation of cells is maintained in the substrate. So I would like to finish with this picture that shows people involved in the research. Taras, you already heard him, and he was present in another part of his work. He was the main driving force of this research. Greta Babakhanova was also a PhD student. We enjoyed collaboration with our colleagues in the Netherlands and in Kent, shown here on the right. And I would like to use this opportunity to say that we are always looking for new graduate students to come to Kent State and to get involved in our research. And this is the conclusion page. I am ready to answer the questions if time permits. Thank you very much.
Thank you very much for a very interesting and valuable talk. And there is a question from our chat. Dr. Leonid Dolgon from Estonia asks, Dear Oleg Dmitrievich, please comment, did such nanopattering of alignment changes the temperatures of phase transition for usual pneumatics for elastomers?
Well, the gradients are small as compared to the typical length scale of the pneumatic. So if you would see the picture, you would realize that the orientation changes over the scale of hundreds of micrometers. So it's too weak a change for the phase transition temperatures to be affected. But when it comes to the tissues, then of course the curvatures are at the scales that are comparable to the size of individual cells, biological cells like fibroblast. And there, as you saw, the phenotype of cells is being changed by the orientational order.
Thank you very much. And an additional question also comes from Leonid Dolgo. Could those spikes in alignment in nanoscaled areas can be used as a kind of nanothermometers?
Yeah, in principle, yes. Yeah. Yeah, this amplitude is directly related to the temperature, right?
Mm-hmm. Perfect, thank you. And the next question for Professor Holchansky. Dear Dr. Lavrentovich, would it be possible to seed and grow cells on the changeable LC surface? Have you tried change LC orientation and how cell structure reacts?
Yeah, exactly. This is what we are trying to do right now. It's the question right on the target. You see, it's very difficult to grow tissues on the substrate that is dynamically changing. But we know that for the real situations, the cells are always located at something that is alive and moving. And so far in biomedical field, it's a big problem that people cannot have the dynamic substrates. And we hope that with the development of Lie crystal elastomers as the substrates for the growth of cells, we could now produce dynamic control of the growth of tissues and cells by changing the profile of the elastomeric substrate.
Thank you very much for answers and also again for interesting talk.
Yeah, thank you very much.
Thank you for your talk.